Okay, so far we have been discussing type checking, and we said that type checking proves facts of the type of the form expression E is of type T. Now, and we also saw an example. Now, when we are doing type checking or type inference, we are basically constructing a proof either to check whether something is of type of the annotated type or to infer the types. And this proof is on the structure of the abstract syntax tree of the expression E. Right. So, for example, when we said what is the type of 1 plus 2, we basically formed an abstract syntax tree which looked like plus 1 and 2, and then we said okay, 1 is of type int and 2 is of type int using the int rules, and then from there we derived that 1 plus 2 is of type int. Alright, so notice that the proof basically has the same structure as the AST. We're first finding the types of the leaf nodes, and then from there we are moving upwards. So proof actually has the same shape of the AST as we just saw. Because it is on the structure of the AST, it also has the same shape as the AST. And one type rule is used at each AST node. So we have a set of type rules. We have, let's say, a database of type rules. And at every node in the AST, we are going to figure out which type rule to use. And we're going to use one type rule depending on our set of rules, and which one matches. And based on that, we're going to identify the type of any internal node of any AST, and from there on, we'll keep moving on. So one type rule is used at each AST node. So here is a more general diagrammatic explanation. So let's say at any point of the AST, we have a node n which has I children, C1, C2, ... Ci. Maybe in my database of typing rules, I have a rule which looks like the following, which says if it is provable that C1 is of type T1, and it is provable that C2 is of type T2, and so on, and Ci is of type Ti, then it is provable that N is of type T. Okay, and this is just a type rule in our database of typing rules, and maybe it has a name. All right. Now, when I'm actually going to construct the proof, so let's say I have some expression, then I would have some actual type. So maybe C1 has some actual type, let's say A1. C2 has some actual type, let's say A2, and Ci has some actual type AI. And then I have to check whether A1 matches with T1, A2 matches with T2, AI matches with Ti. And if so, then this rule can be applied. All right. So only if these types match can this rule be applied. And if the types match, then I can apply this rule and I can infer that N must be of type T. Okay, so we're going to see examples, but this is basically the structure of a type checking system. So types are computed in a bottom-up pass over the AST. So why do I say bottom-up? So any traversal of an AST is basically a recursive traversal where we first go down and then we come up. Recall the 3 steps when we discuss the traversal of an AST. But what is interesting is that the types are basically propagated from bottom up, and as we saw in our example and as we've been discussing. So we first compute the types of the leaf nodes, and from there we build up and compute the types of the internal nodes and the top level node of an expression. Okay. All right. Now I'm going to define the notion of the soundness of a type system. So what does it mean that a type system is sound? Well, basically, informally, intuitively, this means that the type system agrees with the execution semantics of the language. So what do I mean by execution semantics of a language? Well, that is what we understand the language meaning, right? So for example, if I say 1 plus 2, well, we understand that this has some meaning. The meaning is that it's going to execute addition on literals 1 and 2. Similarly, if I say x plus y, then basically it's going to compute the addition operator on the values, the runtime values of x and y. So notice that the execution semantics is a runtime concept, and it basically says, if the program is here, then I evaluate the expression, and when I evaluate the expression, assuming the value, I already know the values of the leaf nodes, for example, x, y, etc. And so from there, I'm going to compute the value of this particular expression, and maybe I'm going to assign it to some other variable or something like that. All right, so that meaning of an expression, I'm calling it execution semantics of a programming language. So far, we understand the meaning of a program already because we've been writing programs, but we understand the meaning of a program rather informally. Later in the course, we're going to define execution semantics in a very formal way, just like we are defining typing rules. We'll also define semantic rules, execution semantic rules. But for now, it just suffices to know that execution, we are just interested in how the language behaves at runtime, or how expressions evaluate at runtime. That's what the execution semantics are. So at runtime, an expression may compute a value v for some existing values of all the leaf nodes, right? So, and maybe it's getting computed over and over again, but whatever it is, it will compute a value v. First time it may compute v1, second time v2, v3, whatever, right? So that's an execution behavior. On the other hand, this type checking or type inference algorithm is assigning a type to every expression. So, we have judgments of the type. An expression is of type t, or what we also say E:t. So this type proof is basically constructed through a bottom-up application of the typing rules on the AST, as we just discussed. And notice that this has nothing to do, at least so far, with the execution semantics. We're just applying the rules. But it's important, however, that these typing rules are in agreement with the execution rules, right? For example, I can't just I can't just have a typing rule in my system which says 1 plus, if 1 is an integer and 2 is an integer, then 1 plus 2 will be a string, right? Or in general, if E1 is an integer or E2 is an integer and E2 is an integer, then E1 plus E2 would be a string. Now that would violate, that's as good a typing rule as any other, because it's just a rule that you're specifying and the checker is supposed to check against those rules. But that rule does not agree with the execution semantics of the language, because in the execution semantics, the plus operator is supposed to indicate addition, and so it's not clear how you could get a string from addition. So the typing rule will not agree with the execution semantics, and so that is where the notion of soundness comes in. Informally speaking, a type system is sound if all the rules in the type system agree with the execution semantic rules. All right. An expression computes a value v. If it is evaluated multiple times, it can compute different values, say v1, v2, v3. But statically, when at compile time, an expression is identified to be of type t. There's a unique single type t associated with that expression. We say that a type system is sound if whenever E is of type T, as determined by our typing rules, then E will always evaluate to a value v1, v2, v3, whatever it evaluates to, whenever it evaluates to. All those values v1, v2, v3 will be such that they may have their own types, s1, s2, s3, and so on, such that all such types of v1, v2, v3, let's say it computes a value v, which is of type s, then s must be a subtype of t, right? So for example, if it computed value v1, which had type s1, then s1 should be a subtype of t. So all values that are ever computed for E at runtime should be of dynamic type S, such that the dynamic type is a subtype of the static type as computed through my typing rules at compile time. So what is the use of a type system being sound? Well, if a type system is unsound, that means if it didn't obey this definition, this rule, then it is possible that a type correct program exhibits errors at runtime. So for example, it is possible that at runtime a variable I, let's say, at compile time I determined that I is of type int, but there is no guarantee at runtime that I will actually evaluate to a value v of type int. Maybe it will evaluate to a value of type character at runtime. And if a type system is unsound, then it's possible that at runtime it evaluates to a type which is different and which is not a subtype of the static type that was identified at compile time. So if a type system is unsound, a type correct program can exhibit type errors, I should say type errors at runtime. Whereas if a type system is sound, then you can be sure that there will be no type errors at runtime. Which means that, wherever the type system determines that I will be an int, you will only get int values at that point for any possible execution of that program. So soundness is very important for that reason, because it basically catches errors early. So if there was an error in the program where a potentially non-int value could appear for I, and then I'm using it in an int context maybe, then that error will be caught at compile time, and we won't have to wait all the way till runtime to catch that error. In general, the soundness of a type system can be ascertained by checking the soundness of each type rule. So if you just look at each of your type rules and check whether it's actually sound, just like I gave you the example of the add type rule. So indeed, this type rule is sound because the execution semantics of the plus operator agree with this particular type rule. Okay, in our type system, we only want sound type rules, but it's not just enough to be sound. We actually want precise type rules as well. All right. So some type rules are better, and by better I mean more precise than others. All right. So here's an example. One of my type rules could be that if 1 is an int and 2 is an int, then 1 plus 2 is a void. Now, is this a sound type rule? Well, I've claimed that this is a sound type rule. All right. Let's look at another type rule. It says if 1 is an int and 2 is an int, then 1 plus 2 is an int. Is this a sound type rule? I claim that this is also a sound type rule. So why do I claim that both of these are sound type rules? Notice that I'm assuming in my language that void is a super type of all other types. And so anything I compute will always be of type void. And so it is sound. I cannot contest the fact that this is sound. Because void is a super type of int, and by definition of super type subtype, any value that gets computed is actually of type void. And so this type rule is actually sound by a definition of soundness. But it is not very useful. In fact, this rule is more useful, right? Because this is more precise. It's not just saying that it's void, which is true. It's also saying that it's actually an int. It's going to be an int. So it's saying more than what the first type rule is saying. And so while the first one is sound but imprecise, the second one is sound and more precise. And we want the most precise possible thing in our typing rules, because that will help us accept more programs. So for example, if this was my typing, if the first one was my typing rule in my type system, then if I have a program which says 1 plus 2 plus 3, this would be rejected by the first type system, but it would be accepted by the second type system. Why would it be rejected by the first type system? Well, the first type system would infer that 1 plus 2 is of type void, and then I can't use plus on a void, right? So that won't I won't have any type rule which says, if E1 is of type void and E2 is of type int, then what should be the result? I won't have a type rule, and so my type check would fail. On the other hand, if I use a second rule, then that type check would succeed. So if I have sound rules, it would still accept all the programs that it accepts would still be correct, but it would leave out some incorrect programs, right? It will leave out some correct programs. So if the type system is sound, then it only accepts correct programs. However, we want precise type system, because if it's imprecise, if it is not giving the full information, then it's also going to exclude some correct programs also, which we don't want. So the second one is sound and precise. The first one is sound and imprecise.